detail. I guess I'm gonna do my best. These have been a second for me. The math I'm okay with for the most part. It's a little bit of the sciencey part that I'm a little rusty on, but okay, these are the steps, and these notes are posted on our week at a glance. So if you don't want to copy all this down step for step right now, that's fine. But am I sharing my screen? Yeah, okay. Always forget to push that button for whatever reason. Tesla's got to remind me like halfway through an explanation. You don't think you're sharing your screen? Oh, of course I'm not. Okay. Happy virtual teaching. Okay, so these are our steps. So generally what an ICE table stands for is it's called initial change and then equilibrium. So basically you're looking at where the reaction initially is at. You're going to predict which way it's going to shift and make changes, what's going to get added or subtracted to whichever side, because the reaction can go both ways. And then your answer is like, okay, here's where we're at equilibrium, and then we're going to do some algebra business to find missing pieces of information, kind of similar to what we did the other day. But we're going to organize all of our stuff into what's called an ICE table, initial change, and equilibrium, E for equilibrium. Crazy. We're in that unit, that's what E stands for. Like, I don't know why I couldn't think of that. Okay, so this essentially gives us a way to find missing unknowns and make predictions about a reaction that can happen in both directions. And it is a little bit math heavier, so just brace yourself. But we got 3 examples that we're going to look at. So this is the one we started with the other day. So I'm going to kind of just talk back through this one a little bit and then see what questions you have before we actually fill in the numbers on the table. So, okay. Tristan checked our equation the other day and it was balanced. So we do always have to check that. I mean, I don't trust, the College Board to give you balanced equations every time. I don't know much about the AP Chem exam, but I would assume that you're going to have to balance an equation at some point. So this was our reaction and it was all ready to go. And we had carbon monoxide was reacting with with steam with water to produce carbon dioxide and hydrogen. They did give us the equilibrium constant, so they gave us the K value. So we did know that. So we knew K is going to be this number in the end. And we want the concentrations of all of the things involved, basically, at equilibrium. So right now we're not at equilibrium, but we want to get there and figure out what the concentrations would be at equilibrium. So that's what we're kind of going to do. So what we want to do is write our K expression out, because that's where math is fogging up today. Oh, good. Give me a second. Glasses and math. Okay, so what we want to do is we're going to use this. This is where the algebra is going to come in at some point, is we're going to have to solve for some stuff. So we do want to write our expression, and we do know it's equal to 5.1. The other thing we know is right now how much of each thing we have, or initially how much of each thing we have. So this one's an easy one just to get us kind of warmed up here, but we have 1 mole of each thing and then in 1 liter. So since concentration is moles over liters, everything is 1/1. So all of my concentrations that I'm plugging in initially are going to have a concentration of 1. So I can fill that number in on my initial row here, because I do know initially right now where everything's at, concentration wise. And Q tells me like where I'm at in terms of, all of these concentrations. It's like a little snapshot in time of where the reaction is. So right now Q is 1. So if I plug 1s in, obviously for all my things there, and multiply 1 together and divide by 1 and all that, I'm going to get 1 for my answer. So on Monday, we talked a little bit about Q versus K, or I guess a lot about that. And right now, Q is less than K. So if Q is less than K, that's going to tell us our reaction is going to shift in the normal direction. So from reactants to products. So basically, I don't have enough products, or I have too many reactants. I need to make some more products to balance myself out. So when Q is less than K, you're always going to shift in the product direction, so you're going to make more products. So the reaction is going to move towards the product side. You're going to start cranking out CO2 and H2. So once we know which way the reaction is going to shift, spoiler alert, they're all going to shift to the product side today. I'm assuming the examples we're going to do after break are going to go the other direction. I just haven't looked that far yet. So for now, this is the traditional direction. So when we write the change, we're going to put subtractions on this side because we're going to minus products away or minus reactants away to make products. So I'm going to add some kind of number here. Now the problem is I don't know where, I know what the final number is for this equilibrium constant, but I don't know like how much stuff is reacting away to get me there because I don't know what the concentrations are yet. That's what I'm trying to find. So this is where the algebra comes in. We're going to put X's in for the stuff we don't know. Those are the change in concentration for each of the things. I don't know that. And then here's where I arrive at equilibrium. So if I started with 1 molar concentration of the stuff, take away the stuff that reacted for this one, and I take away the stuff that reacted for this thing, the water. And then here I'm going to add some products, and here I'm going to add some products. I'm going to need to make more space. It's going to need to happen. So this basically tells me, I'm going to put little columns here because that helps me. This tells me that I've got each of my 4 things. I know I'm subtracting some stuff from the CO2 and the H2O. I'm going to make some stuff on the other side. I just want to figure out what these concentrations are, so I'm going to have to solve for X, which is going to get a little dicey. It's not terrible though. It's not terrible. We're going to do that part. So up to now, I've said a lot of words. Mostly, sometimes I have to say the words to make sure I remember what I'm doing. This has been a while. So what questions do we have? Drop them in the chat, people at home, or you can hit the raise hand button. And I could call on you. That's another option. Or you can just like unmute, shout at me. Yes.
The Q is bigger than K, would you add reactants and subtract products?
That's a great question. So yeah, this was flipped around. So you're saying if instead we had to shift in the other direction? I think so. I'm pretty sure. I need to look it up, but I'm pretty sure. Today's examples don't go that direction. So right now we're not going to worry about it. Yeah, we won't get to that too much. Thank you. I believe so because I have to go back because I'm a little rusty, but this can go both ways. So I'm pretty sure if we decided, oh no, we need to shift in the reactant direction, that means we're going to subtract on the product side, add to the reactant. We're going to kind of flip what we did. I'm pretty positive, but I'm going to verify that. So, because these can go both ways. Any other questions? Anything in the chat today? People at home saying a lot of words. Anyone else in here say anything? Okay. Sometimes I get excited with math, so if I need to slow down, just shout at me. Hello, Marley. I see that. Yes. Thanks for joining. Okay. So now what we're gonna do, Morgan, hold on to your hat. We're gonna do some algebra. Okay, so I'm gonna take all this crap and I'm gonna plug it into this thing. So I'm going to flip to the next slide, and because these represent the concentrations of where I'm at equilibrium, but since I don't know how much is disappearing and getting added, I have this like expression instead that I'm going to plug in here, which is a little gross, but we can do it. I'm going to take a screenshot of that because I don't want to write that again. Okay, put that there. Okay, so I'm going to take each of my things. The CO and the H2O are 1 minus X, and the top is 2 of the same thing, 1 plus X. And the whole thing, we're going to put it all together. So we've got K equals 1 plus X times 1 plus X over 1 minus X times 1 minus X. And that's all going to equal 5.1. And now I just have to solve for X. Looks kind of gross though. So here I'm going to show you guys something. This is x plus 1 times itself. So we can just say x plus 1 squared and x minus 1 squared. Those are both multiplied by themselves. So something times itself is going to be that thing squared. And then anyone online, feel free to drop it in the chat, or people in here. How do I undo a square root? This is the square root trick, I guess. How do I undo a square root? How do I undo a square? Sorry. Yeah, what do you think? What do you think the answer is that I gave away already? You're gonna square root both sides. Yeah, you're just gonna square root this whole thing and you're gonna square root that number. I don't know what the square root of 5.1 is, so if somebody has that, type in. They would have. We're gonna do 3 today that I believe that I understand. So no. You have to embrace this. This is so we want to undo the squares. So I'm gonna square root. So now it's gonna look like x plus 1 over x minus 1. Okay, so now we're gonna do more algebra. So now we're gonna cross multiply. Yep. Welcome to math. AP Chem, I mean. Okay, so now we're gonna cross multiply. So I always imagine this is over 1. So this is like 1 times that junk. So that's gonna just stay x plus 1. And then this is 2.258 times that junk down there. So I'm going to write that. 2.258 times x minus 1. Okay. Who has a question up to now? Because there's some algebra coming. Yes, ma'am. Probably. Yep. Hold on. I turn things around a lot. I teach stats now, which is just a lot of writing that I just kind of forget. I don't know. I turn my numbers around now. Well, that won't matter. Addition won't matter. This one does. Sorry. I start switching things. X minus 1. There we go. 1 minus x. 1 minus x. I swear I know what I'm doing. Okay, I do have a teaching degree. I worked hard for it. Okay, thank you, Emma, right? Okay, good. Okay, does anyone have questions about anything up to now? I don't want to go too fast because this was in college where I started throwing things. I did not care for ice tables myself. There's a lot of steps. They're kind of hard. There's just a lot of parts. What questions do we have? Does anyone else have questions in here?
So is every problem going to be like this?
They're a little lengthy, yes. Yeah, I'm gonna need a few more slides. Okay, here we go. We're gonna go ahead and do this number. We're gonna distribute it. We're gonna multiply it through. And I'm gonna get rid of these parentheses here because we don't really need them, but so we've got x plus 1 equals 2.258 times 1 is that number minus 2.258x. We need to get the x's together. So I'm gonna add 2.258 of the x's to both sides. Running out of space. Okay, so I have, sorry, think this through. So I've got one of the x's here, so I'm gonna have 3.258 x's now, plus 1 equals 2.258. Why didn't I round that number? Okay, and now I gotta subtract the 1 from both sides. I'm just solving for x. So this is like back from the Algebra 1 days. Maybe block those out of your mind. I don't know. 1.258 and x, and then I've got to divide away this number on both sides to get x finally by itself. And so X is going to equal something. Does anyone have a final number for me yet? I heard people typing out a calculator.
I got 0.3.
That's what the key has. That's what the key has. We did it. Okay. Yep. All right. Give me two seconds. We're gonna get with me. All right. Here we go. Marley, let me look at your question. Because is this referring to the typo? Why is the X negative in certain parts? Is this referring to the mistake I made before I corrected it? Maybe.
Oh yeah, you did.
Okay. I'm not sure. Okay. Why is X negative? Oh, okay. Well, maybe let me try this. Okay, let me go back. So right here, Marley, if you look at the meet screen, this might help other people too. Let me erase a few of these lines. Getting a little too extra. So we had to decide, maybe you missed this part. That might be it. So we went through and found Q. So they gave us a concentration. And so we plugged those in, or in the moment concentrations, which told us, we're at 1, which means we have way too many reactants because Q is less than K. So kind of what we talked about on Monday. So that told us we're going to shift in the product direction. I've got too many reactants. I need to get rid of some of them. So that means that's where the subtraction came from. So it's like I started with 1. The concentration here was 1, and I'm going to lose a certain amount of that. I'm going to reduce the concentration on that side because it's shifting in the product direction, which is where the minus came from. Does that help? Oh, okay, good. Yeah. All right. Okay. Are we done yet? No, we're not done yet. That would be too easy. So now we have to go back and look because we found X. What the heck did X stand for? Well, X was how much we lost on this side for each of these and how much we gained on this side for the products. So we just have to plug X back in here and get our final amounts. So if I do that, I'm plugging X back in so I can get each of my things. So for H2, I've got 1 plus X, so that's going to be, right? Yeah, 1 plus X, so 1.386. That's going to be the same. No, yep, I'm going to turn it around. I can feel it. Okay, then 1 for CO2, it's going to be 1 plus X again, so 1.386. For the bottom parts, that's the reactants we lost on those, so 1 minus 0.386. Which I'm going to cheat and look at the key, is 0.614. And then same thing for the other reactant was also 1 minus X. Okay, who has questions? Because I just did a whole lot of things, and I don't feel super confident that we all know what just happened. Maybe we do though. That would be great. But there's a lot of stuff that just went on. I'm going to block off the final answer here. Sorry, I got a little crazy with the writing. There's our final answer. That was the goal, is to figure out now at equilibrium, these are the concentrations I need. That was the crazy way to get there. What questions do we have? People at home, definitely feel better with another example, but I think I sort of understand. Okay, yeah, same, girl, same. The next one's a little slightly different, but sort of the same, yeah. Okay, on this one, okay, so we just, anything. I mean, I could keep going. This might be one of those moments where it's like, maybe I get it, but maybe I need to see it again. Great. Okay, I got 2 more do agains, and then I'm out of do agains because that's as far as I printed from the other teacher at Grand River, bless her soul. Okay, so let's try another one. This one's a slightly different. I mean, it's the same setup, but our algebra might be a little different, I think, on this one. Okay, so let's try it again, and then I can always talk back through any of these examples, obviously, because there's a lot happening. Okay, so example 2. Okay, Oh boy, hold on to your hats. All right, so first step, we gotta check to make sure the equation is balanced. So somebody, do I have Tristan? Do I have him? Does internet work? I don't know, I don't think I do. No, I don't. Okay, is my equation balanced? That's step one, so we gotta check this, because if it's not balanced, I'm gonna have a real bad time, with all the algebra. I believe that it is, so, yeah, it does look balanced. Okay, step one done. Woo. All right, we're gonna write our equilibrium expression. So at equilibrium, we wanna write out our stuff. So products over reactants. So we got this stuff here is going on top. Just remember, any coefficients become an exponent. So because this has a 2 in front, the SO2 has a 2 in front, you got to put that as an exponent. And then O2 is there. So, and then our reactant SO3, and that's going to be squared. Okay, so boom, we wrote our equilibrium expression. That's the ratio of the products to reactants at equilibrium. So I did that. Now we got to read the question and see what we've got going on. So in this case, we have initially the vessel charged at, I don't know, that temperature. I don't ever think we really need temperature ever. I'm going to say that lightly because I'm not totally sure either, but right now we don't. Okay, we have a partial pressure of 0.5 atms. At equilibrium, the partial pressure of SO3 is 0.2 atms. Okay, yep, I got panicked for a second internally, but I think we're good now. All right, calculate Kp. So this one's same kind of setup. We do have to get Q. So we're gonna have to do that. Okay, yep, I got it again. Sorry, my brain sometimes I get a little. Okay, so we have Kp this time because we have all gases and they gave us pressures. So let's go ahead and get Q. Now the issue here is they've only given us a pressure. I actually wrote this wrong. Sorry. I'm sorry. Okay. I'm here. Sorry. I'm sorry. I forgot we were doing pressures. Oh, okay. Sorry. Just notation pickiness is all. Sorry again. I just feel like I need to keep saying that. I don't know why. I feel like you just wrote all that down and I'm making you erase it. Oh, okay. Sorry, pressures. I just keep doing it. Just gonna keep saying sorry. All right. Okay. There we go. That's just notation because we were in pressure. Now the only thing on this one is they only gave us the pressure of a reactant, which means my only option, I can't calculate Q because I only have reactants right now. I don't have any pressure or any product stuff. So I don't need to calculate this one because again, you only have a reactant. So that automatically tells you the reaction's going to go from reactants to products. Like that's all we got. We got to start the car and drive it before we can put it in reverse. So let's go ahead and, so we got that. Okay, so we're gonna have to set up our table. So 2SO3. So, and then 2SO2 plus O2. Okay, initial, whatever changes, and then we're at equilibrium. I think, I hope, yes. So initially, they gave us a pressure of 5 atms. So that's our initial pressure. And then at equilibrium, they're telling us the pressure of this thing is 0.2. So in order to make products again, I know I'm going to add a certain amount over here of SO2. I'm going to eventually add a certain amount of O2. I just need to figure out what that amount is. So I also know I'm going to take away a certain amount on this side to make the reaction happen. We always lose reactants, we make products. The only thing on this one that is different is we've got some coefficients here now. So I have certain ratios that things are happening in. So for every 2 of these, I'm gonna make 2 of these and 1 of those every time. So because I've got these little coefficients here, that's telling me like, yep, something's gonna go away on this side, but twice as much as it is gonna make this stuff. And same with this. So 2 times, we gotta put those 2's in front. So you just have to copy these down if you do have numbers. Okay, so who have I lost? I feel like, I don't know, maybe I'm just being self-conscious. It's a lot to just think through and teach, like, when you're wigging it. Okay, so what are our questions? Probably should have more confidence. I just told you, Morgan, to have confidence, and I'm sitting over here babbling to myself. Okay, we're not done yet. Don't ask that question. We're just pausing. We set up the ice table. We did that. Okay, yep, all right, so now initially I don't have any products, so I'm gonna put zeros there, just because, I know they only gave me reactants to start, so we assume we have no products yet. So here, if I add these together, this column, I'm gonna get 2x. If I add the O2 column together, I'm gonna get an x, 1x. And then I gotta plug everything in. I gotta do the algebra part. So we are here now. So I'm gonna plug in what I know, I think. Yes, I'm gonna plug in what I know. Am I gonna do that? Yeah, sure. Okay, just making, okay. So now in terms of like, what am I solving for? Well, you could plug all this crap into here. But if it were me, we just need to get x somehow. X is gonna be the same number all over the place. So what my brain is zeroing in on is this part. Because this tells me I can write a little equation out of this. Yes, ma'am. What did I mess up? Okay, good. What's your question?
If it's asking for the K at 1,000 Kelvin, is that different? What do we have to do it different?
No, the temperature, as far as I'm aware, has nothing to do with anything right now because the temperature stayed constant. If the temperature were to change, that would change the gases moving back and forth because like they're gonna get more excited, they're gonna bump into each other more, the reaction's gonna speed up. So I don't believe we have to do anything with that. Yep, it stayed the same, so it's not gonna influence the reaction in any way. But good question. That could change later. I don't know. I didn't look that far yet. But what we have to do is write an equation. So since Morgan doesn't like plugging all this stuff into here, I just figured we'd do an example where we wouldn't have to do that. It totally planned that out. So I'm going to say, okay, 0.5 minus 2x should equal this number. I mean, that's what they gave me. They said at the end of the reaction, once we're bounced back out, this is what I should get. So now I just have to solve for x. I have an equation, and then I can plug x into other spots and figure everything else out once I get it. So if it were me, I would add 2x to both sides because I don't like negatives in front of my variables, but that's just me, I guess, maybe. So then I've got 0.5 equals 0.2 plus 2x. And then I'm going to get rid of the 0.2s on each side. And that, what do I have? 0.3 equals 2x, right? And then divide by 2, we should have 0.15. So then I know what x is, so then I can figure out at equilibrium the pressures for each of these other things. So the pressure here for SO2 is going to be 2 times 0.15, so 0.3 ATMs. And then this one, pressure of O2 is just X at equilibrium, so that's going to be 0.15. The blue stuff here is kind of your final answer of your pressures at equilibrium. Which middle number? 0.3.
0.3.
0.3, yeah, sorry, I have a really crappy stylus. It's very cheap on Amazon. No, Mr. Russell has a fancy Apple Pencil. And it does write really well, but it's like $100 and I'm way too cheap. Yes, Morgan, what's your question?
Why do we use square root?
That's a wonderful question. I'm so glad you asked. Why did we have to use a square root? We had more crazy crap going on, basically, but we had expressions in here. So this time on the first example, I wasn't given any numbers in this row to start, versus the other one, they already told me, okay, at equilibrium, you know what the pressure is of this side already. So on this one, I didn't, so it created expressions here, which ended up getting multiplied together, and then I had to square root all that. The algebra was just more intense. This one was nice because I could just go, oh, wait a second, there's an equation I can write. This minus that should be 0.2 and solve away. What questions do we have? We have one more example. Ooh. Oh, do they want KP? Yes, they do. Sorry, I wasn't done yet. Thank you. Okay, sorry. Yep, we got to get an actual final number for KP. It's like somebody read the question. Thank you. Okay, sorry, we got to plug and chug. So we got all our parts. I stopped a little early. They do want us to get a KP number. We just got to plug our parts in. 0.3 times 0.15 over 0.15, and whatever that is going to be your final answer. So plugging in our numbers. Oh, square it. God, square the bottom one too. Oh, I don't know. Hold on. Sure. No. Yes. Just a second. What day is it? Okay. Yep. Sorry. I swear I looked at the key. I was like, I think I could do this. I can do this. Okay. Yep. Sorry. I'm plugging in the wrong things, but okay. So we have 0.3 squared, this number, sorry. 0.15, and then the bottom number, sorry, this thing. Then square it. I got the square this time, Josie. I did that. Okay. That's whatever that ends up being, is gonna be your final answer. Let me erase a little bit of this and make more space. Jamboard's not very big. It's one downside. Okay, questions. Sorry, these are very long. This is gonna be your final answer. No. Yes. I already turned the paper. Yes, 0.3375. The key says 0.338, which would be rounded, but yeah. You did the calculation. Okay, what questions? Sorry, this is a lot of stuff, and I got a little not lost, I just kind of stopped. What percentage? Oh, I just learned that too. 7 to 9, I think. Okay. 7 to 9%. 7 to 9% on the AP exam, I believe.
Well, the problem is that I don't know what works to do.
7 to 9%.
Yeah, because we're in yeah, but if you just throw some numbers at me, I'll be like,
Okay. Questions? Any questions from people at home before we dive into one more crazy adventure together? Oh, Morgan's gonna love the next one, right? Gonna love it. There's a square somewhere. Okay, and like I said, once we get through all three of these, I can go back and, if there's any other lingering questions while you're looking through and it just hasn't come to you yet, I can go back and try to talk through it all. So, okay. Okay, this one's real good. Yeah, we gotta write the equation for this one. All right. But if we look, we're gonna use the zero trick. We're just gonna pretend x is 0 at one point, and a bunch of stuff's gonna go away. So, okay, let's go ahead and do this one. We're gonna wrap it up. This is it. This is it. These are kind of a doozy. Okay, so gaseous NOCl, whatever that is, decomposes to form gases NO and Cl2 at 35 degrees, which to my knowledge right now, that's extra information we don't need as long as it stays the same. The equilibrium constant is that number. In an experiment where 1 mole of NOCl is placed, oh boy, in a 2-liter flask, what's the equilibrium concentration? So let's first of all just get the equation written. So right now, I know NOCl decomposes, can go back and forth apparently, to make these 2 gases, NO and Cl2. And we're going to have to make sure it's balanced. I don't believe that it is. I think we need a 2 here. So we have 2 chlorines on that side, and I'm going to need a 2 there. Now I think it's balanced. Yeah. Okay. All right, so that's our equation. Copying the things. It says it decomposes, so I know this is a reactant, and I know it makes this stuff, so these must be my products. Any questions on writing the equation from scratch? Because, you know, why not throw that in at this point? I don't, anything at all. Okay, all right, so we did that, check. We got to write K out, equilibrium expression. Let's get that out of the way. We do have, it looks like no pressure is given. It's going to be moles and liters and stuff. So we're going to write concentration stuff instead of pressure stuff. So Cl2 times NO. NO gets a square because there's a little 2 in front of it. And then NOCl squared. Boom. So that's where all the things would go. That's where all the things go. Okay, on this one, we have okay, so we have to get Q. We're here now. So they gave us some things. Let's see what they gave us. So in the experiment, we have 1 mole of NOCl in a 2-liter flask. So I'm only given a reactant again. I don't know any product. So I'm going to kind of start setting up my table here just to get things organized. So initially, I'm given a certain concentration of this stuff. Now, I do need to switch this into moles per liter. So 1 mole divided by 2 liters. Max, what's 1 divided by 2? That's a 0.5, yeah, it's a big old half. So I have a concentration here of 0.5. So that's a quick note, moles per liter. So I do have to do 1 divided by 2 because this is 2 liters. Before it was just 1 liter. It was 1 and 1, which was nice, but that's why would we be nice on every question? We're not. So, so I'm only given reactants again. Yeah. Yep, that's it for there. So I'm not going to have any products yet initially. They just gave me that. So there is no Q to calculate, again, because if we only have reactants, that means the reaction is going to proceed like it normally would, reactants into products. Got to start the car before you can put it in reverse. So then if the reaction's going to do that, we're going to have to start setting up our table. So we're now here. So I know I'm going to lose a certain amount of my reactants. I know I'm going to make a certain amount of my products. There's something I have to put in this change row, though, that I did on the second example as well. Is it a 1-to-1 ratio between all my things, or is it different? Like for every one of these, am I making one of those, or is it a different amount? Emma, what do you think? Go on. I don't think my phone's ever rang this year. That's why I stuck it back here. Oh, she sure is. Yeah. What was that? Bye. Farewell. Guys, my phone rang. It was the first time it's rung in like 3 years, I think. Everyone just sends G chats. Okay. All right. We have to put in the coefficients here because that's going to matter, because things in chemistry, it's just like baking a cake. You can't, you've got to have certain ratios of things. So we have to account for that. So there's 2 of the NOCLs always make 2 of the NOs, and 2 of the NOCLs always make 1 of the Cl2s. So we just have to account for those things in our change row. Yeah, that's it on that part. Okay. Now I gotta go down. I gotta write, okay, so now I have to write what's at equilibrium. So I know I had 0.5 of these minus 2 x's. That's gonna be the result in that column. This column, 0 plus 2x, I'm gonna end up with 2x. And here, 0 plus whatever change, I'm gonna end up with an x. And this is where the algebra is gonna come in. It's kind of gross. It's not great. We can do it. Okay, I'm gonna move this. Okay, so now I'm gonna plug all this crazy crap into my expression because I don't know what x is. I'm gonna have to stick it in here because they did give me a number right here for k. So let's go on an adventure. Here we go. We're gonna put our numbers in. So k is 1.6 times 10 to the negative 5th. I'm just gonna write this as a decimal because it helps me. So 0.000016 equals this stuff on top, so this stuff here. Nope. Well, I guess it doesn't matter. 2x squared times x all over this crap on the bottom. And that gets squared. And now we have to do algebra. Morgan, what do you want to do?
Well, a lot of things, but would we cross multiply? Are we not?
Yeah, we could, but
We're not.
yeah, we could do that. That's just kind of gnarly. So I'm not entirely 100% sure why this trick works, but this is apparently a valid trick. This is called the 0 trick, and I can elaborate on it a little more when I learn a little more about it. But basically, this is strange. We don't want to. Do you remember foiling from Algebra 1? We do not want to foil that out, and yeah, it's too much. So what we do is we pretend x is zero, and this gives us a close enough estimate that we feel okay about. So I guess. I will delve deeper into why this is a valid trick. I just didn't quite get to that point. I could get you through the math the rest of the way though. So we're gonna assume this is 0. So this kind of goes away, and then basically it's not gonna offset too much, I guess. It's still gonna give us a good enough estimate of what's happening at equilibrium. So on the bottom now, I just have 0.5 squared. So there's a lot happening. So let me rewrite. 0.000016 equals. I'm gonna square this. I'm gonna square this. There's a number and a letter. I'm gonna square that. That's gonna be 4x squared times this other x, all over 0.25, or 0.5 squared is 0.25. I'm just going to get that out of there. What is x squared times x? X to the third. Okay. 0.000016 equals 4x to the third, all over 0.25. Oh, we need to keep going. All right, so we got to multiply both sides by 0.25. Somebody help me out with the left side here. times 0.25. So those go away. And I need a number on this left side, if anybody has it. Oh, I have my key, trusty key.
Is it
A really tiny number.
0.00004?
Yeah,
I think there's 5.
there are. That's okay. So that's that side, and then I have 4x to the third. Oh my gosh, what do you want to do with the 4, Morgan? What do you want to do? It's being multiplied.
Would we divide it? Yeah.
Yeah.
I'm just waiting for the square root to happen.
Oh, it's not gonna be. It's not gonna be a square root. It's gonna be a cube root. Okay, I don't. What's 0.000004 divided by 4? But I got a root.
1. All the zeros and
Okay.
then
Okay. So point. Well, that would make sense. So 0.00000 equals x to the third power. This is where crap gets funny. We have to cube root. So on your calculator, I don't remember how.
just figured out how to do that this year.
Yeah, I don't remember how fancy your calculators are. I think mine is an old one. So
Mine is math 4.
math what?
Math 4.
Math 4.
On my calculator. That should be.
Okay, I think on your graphing calculators, you can do that, but when in doubt, you can always rate, like, to cube root something, it's taking this number and putting it to the 1/3 power. That's what I used to have to do it. Now I feel old. But I think your calculators now allow you to do a number in front of the square root, like a cube root. Oh, okay, I'll try to figure that out. But anyway, we're gonna cube root both sides. These Jamboards need to be bigger. And then I think we get this number, x equals 0.01. Okay, if you're not sure how to cube root, I can hang out for a second after and I'll pull up one of the newer graphing calculators and look at it. Oh, is that our final answer? Nope, it's not. All right, so now we got to find the equilibrium concentration. So we got to take this number and stick it back in here and here and here, and then you will get your final answer for each of those things. And those are ice tables. So when we get back from spring break, you have practice set 3, which is posted with a key already, so you can see all the problems worked out. I know these are pretty intense. Is that a bell? So do your best today and tomorrow on them, and then we will try to review them and practice them more when we get back. So have a wonderful holiday, spring break, all of the things. Stay safe, don't catch the COVID.